Okay, I think we can begin today's session. Today is the week 12 of the live interactive session of Introduction to Atmospheric and Space Sciences. So today, actually, this is an extra session. We usually have our sessions on Saturday. Yeah, can you mute yourself actually? Yeah, thank you. Yeah. So basically, we have our sessions on Saturday. This is an extra session, which I thought will be helpful in revising the concepts that we have learned so far. So this session will basically be a revision kind of thing. So since you have your exams on 24th or something, I guess. So this will basically be a revision um, kind of thing. So we will be discussing mostly the topics that we have already covered in the earlier sessions. So mostly some numericals and some multiple choice questions will be discussed in this session. So to start with, uh, we will start with a numerical. So the question is, calculate the average density of the layer between 700 MB to 500 MB of the height of the 700 MB surface is 2898 meter and the height of the 500 MB surface is 5370 meter. So as you can see, this question is from the initial sessions that we had discussed regarding different pressure levels, different heights, how the pressure varies vertically and all those things. So basically the question says they want to calculate the density between two layers in the atmosphere. So the layers they have given, the lower layer is the one which is at a higher pressure, that is 700 MB. And then another layer is there above it, which is at a pressure level 500 MB. And they have also given the height corresponding to these pressure levels. The 700 MB layer is present at a height of 2898 meter from the surface, and the second layer, which is 500 MB layer, is present at a height of 5370 meter. So basically they want to calculate the density of the layer between these two surfaces, these two pressure surfaces. So delta P is given, and which is basically 700 minus 500, that is given. Then delta Z is given, the height corresponding to these pressure surfaces with respect to the mean sea level is also given, which is basically 2898 minus 5370. Then we want to calculate the density. So what is the relationship that deals with, that gives you a relation between these three parameters, which is delta P or dP, then delta Z or dZ, and the density of the layer. But if you guys remember, the question is basically the relationship between pressure, height, and density is basically known as a hydrostatic equation. So we have learned this before. So the hydrostatic equation basically is the balance. Hydrostatic equation or hydrostatic balance is basically the balance between the net upward force acting on a thin horizontal slab of air due to the decrease in atmospheric pressure with respect to height, and the downward force that is acting due to the gravitational attraction. So if we consider a thin slab of air, one force that is acting on the slab is upward force, which is basically occurring due to the decrease in pressure with respect to height, and the downward acting force, which is basically the gravitational attraction. So the balance between these two forces is the hydrostatic balance, and the equation is basically known as a hydrostatic equation. The equation says dP by dz is equal to minus rho g. So this has the parameters dp, dz, and the density. So basically, we are going to use this equation to solve this problem. I'm sorry, but can you mute yourself? Yeah. So these things are given. So we are going to use the hydrostatic equation, which is dp by dz is equal to minus rho. So this is basically the hydrostatic equation. So dp, so basically we want to calculate the density, right? Rho. Rho is basically minus 1 by g dp by dz from this equation, which is minus 1 by the value of g, acceleration due to gravity, is 9.8. The value of dp is 500 into 10 raised to 2. So in the question, the unit of the pressure surface is basically MB or millibar. So we have to convert it into SI unit, which is Pascal. So basically 100 millibar is equal to 100 MB is equal to 1 bar, or 100 MB is equivalent to 100 hectopascal, uh, is equal to 1 Pascal. 1 Pascal is equal to 100 hectopascal or 100 MB. So we have to multiply with 100 to get the values in the unit of Pascal. So it will basically be 500 MB minus 700 MB by the corresponding height, which is 5370 minus 289. So if you calculate, this will give you yeah minus 1 by 9.8 into 50,000 minus 70,000 by 5370 minus 2898. It will basically give you the value of 0.82, and the unit is kilogram per meter cube. It is density. They have asked us to calculate the density of the layer of the air between these two surfaces. So the unit of density is basically kilogram per meter. So this will be the answer. So just as a tip to know if your answer is right. So this basically gives you the density of the air, right? So density of the air at the surface, or density of the air, is basically having a value of 1.028 kilogram per meter cube. So just check once you will get the answer. Just check the answer is if it is realistic. The value is nearby this value 1.028. So in this case, we have gotten a value of 0.82, which is basically close to the density of the air. So we have got the right answer. Okay. So that is the first question. Now, so that was basically regarding the hydrostatic equation, pressure levels, density, and all. Now, this one is basically regarding the forces that we have learned, like the forces that is acting on the Earth's surface due to the rotation, due to the accelerating frame of reference, and all those things. So the question is basically two balls of diameter 4 centimeter are placed 100-meter apart on a frictionless horizontal plane at 43 degrees in the northern hemisphere. If the balls are impulsively propelled towards each other with equal speed, at what speed they should travel so that they just miss each other. So the question um, is basically there are two balls of 4 centimeter diameter. So this is one ball and this is another. So the diameter of both the balls is basically 4 centimeter. This is 4 centimeter. This is also 4 centimeter. And they have been placed on a horizontal plane at a distance of 100 meters. So the distance between the balls is given as 100 meter. And this thing, the whole setup is actually at a latitude of 43 degree north. So now these two balls are propelled towards each other. Okay, once these are propelled towards each other, so basically this is happening in an accelerated frame of reference, rotating or accelerated frame of reference, that is basically the Earth. So in an accelerated frame of reference, there will be an additional force due to the rotation of the Earth when the object is moving. So any object having a velocity will experience Coriolis force to its right in the northern hemisphere and towards its left in the southern hemisphere. So we have discussed about these topics before. What are the forces acting on a body even if it is at rest with respect to the rotating earth, and what are the forces that is acting on a body which is actually having a velocity on the surface of the earth. So in this case the balls are actually having a velocity. So the Coriolis force starts acting on the body and the body starts moving. Um, and basically the deviation. So basically it will create a deviation from the initial path. So if the ball is moving like this and this is happening in the northern hemisphere, with respect to the direction of motion, there will be a deviation towards the north, towards the right of the direction. So like this, there will be deviation like this. So this will basically be delta y because this is u and the deviation will be perpendicular to the direction of motion. So this will be delta y. And when the ball is moving like this, there will be a deviation to the right of the direction of motion. In this case, this will be delta y. This is u. So in the case of this ball, the deviation will be like this towards up, and in this ball, the deviation will be down. Um, Delta y will be there. So the question is, the balls are basically propelled towards each other with equal speed, and what we basically have to calculate that what speed these balls should be propelled so that they just miss each other when they are crossing. As they move towards each other, at some particular point they are going to meet each other. So at that particular point it should just miss each other. So like they should not collide, but they should just miss each other. So the condition of they should just miss each other, the distance between these two balls will be basically 2 centimeter distance. Will be 2 centimeter. So delta y should be 2 centimeter if the balls should miss each other. Okay, I think the things are clear. So basically in the question, there are two balls which is having a diameter of 4 centimeter each, and the balls are basically kept at a distance of 100 meter from each other, and the balls are moving at the same velocity. So we want to calculate the velocity. Okay. So now, because this is happening in the rotating earth, what happens is that when an object is moving with a velocity, the object will experience the Coriolis force and will deviate from its initial path. So in this case, since the ball is, and the Coriolis force will always act perpendicular to the direction of motion. So in this case, the ball is moving in the x direction. So the deviation will be in the y direction. Delta y will be the deviation that is happening to both the balls. And in one case, the deviation will be towards the southern part, and in one case the deviation will be towards the northern part. So basically the direction of the the deviation that is created by the Coriolis force will be towards the right of the direction of motion in the northern hemisphere and towards its left in the southern hemisphere. So since this is happening in the northern hemisphere, this will be the direction of the deviation. So now the condition is that the balls should just miss each other. So when they are telling the balls should not collide with each other, when they should just miss each other, the distance between the balls or the deviation of the balls should be 2 centimeter, which is basically the radius, so that they will just miss each other. If this ball from its initial path it is deviating a distance of 2 centimeter and this is also will deviate a distance of 2 centimeter, it will be such that the balls will just miss each other. They won't collide with each other. So that is delta y is given will be 2 centimeter. So now let's try to calculate so we want to calculate u, which is the velocity of these two balls. So let's start with the Coriolis force. So the Coriolis force dV by dt is given by 2 omega u sine phi. So basically the Coriolis force is having an equation Fa cross B, where F is 2 omega sine phi. This is the basic equation of the Coriolis force. We have already discussed these things in the previous classes. Yes. So this is the equation basically. So dV by dt is equal to minus 2 omega sine phi. This is the deviation that will happen. This is the Coriolis force that is acting on the ball. So now dV can be written as minus 2 omega u sine phi dt. Now if you want, we basically want to we have to find u, right? So we don't know what is v. So we only know what is y. So what we can do is we can integrate this equation. So v is basically dy by dt. So if we integrate this, it will become v is equal to minus 2 omega u sine phi into t. With respect to t, we are integrating. Now v is basically dy by dt. Now if we again integrate this equation, we will get y. So y or delta y is equal to minus 2 omega u sine phi t square by 2. This 2 and this 2 will become. Y will become minus 2 omega u sine phi into t square. This is the equation. This is the equation for y. So now here we know the value of so u, the velocity with which the ball is moving, we have to calculate that. So the velocity will be basically distance by time, right? So now since both the balls are moving with equal velocity, the distance that they have to cover before meeting each other will be half of the total distance. So 50 by t. This is basically u. So since both the balls are moving with equal velocity, the point at which these balls will meet each other will just be the half of the total distance. So that is 50 meter, total distance divided by 2. So u is basically 50 by t. So if we substitute this, it will become y is equal to minus omega 50 by t into sine phi t square. So t square and t will be gone. It will be y is equal to minus omega 50 sine phi into t. This will be the equation. So now we know what is y. We want to find what is t. T will be y by omega into 50 sine phi. So y is 2 centimeter as we told earlier. That is basically the deviation that the ball will be having. So 2 into 10 raised to minus 2. It is 2 centimeters, so into 10 raised to minus 2. Omega, which is basically the angular velocity of the earth, is 7.29 into 10 raised to minus 5 into 50 into sine of phi. phi is basically 43 degrees. Sine of 43. This is the latitude. This will give you a value of just 2 into 10 raised to minus 2 divided by 7.29 into 10 raised to minus 5 in 50 into sine of 43. It will give you a value of 8.04 seconds. This is the value of t. Now we know what is t. So was the question? What is the velocity with which the ball should propel towards each other? So we have to find u. That is the velocity of the ball. So u is x by t. So x is the distance that they should cover. That is 50 as we discussed earlier. So it will be 50 by 8.04. This will have a value of 50 divided by 8.04 is 6.21 meter per second. So this is the velocity with which the ball should propel towards each other so that they will miss each other. So we started from Coriolis force, which is dv by dt is equal to minus 2 omega u sine phi. And from that we found out the equation for y. From y, after which is u, which is 50 by t, we got the value of t. Then after calculating t, we found the value of u, which is the velocity with which the ball should propel towards each other. So yeah, about Coriolis force, and the answer was 6.21 meter per second. Okay. So now let's try to do some multiple choice questions. So these are basically conceptual questions. We have already learned these things. So just for a revision, we will just discuss these things. So the first question is, the virtual temperature depends on moisture concentration, dry air temperature, dry air concentration, and all. So if you guys remember what is virtual temperature. So when we were discussing thermodynamics, the value of R that we have already learned in +2 and all was 8.314, and the value was expressed with respect to mole. It was like Joule Kelvin inverse mole inverse. So now when we started coming to atmospheric thermodynamics, we introduced another value of R, which is 287 in case of dry air and 461 in case of moisture. So this R was basically with respect to mass of the gas that is present, kilogram. So this value of gas constant for moist air. So in case of moisture, we mean it is a combination of both dry as well as water vapor. So basically, R basically depends on the type of the gas present and how much gas is present within the parcel that we are considering. It is not like the universal gas constant, it is having a value of 8.314. So in atmospheric thermodynamics, we are representing R with respect to mass of the parcel that we are considering, not with respect. So in that case, the value of gas constant for moist air will depend on how much water vapor exists in the air, how much water vapor is present in that particular parcel of air that we are considering. So every time the water vapor concentration is changing, the mean molecular weight for moisture changes, which is basically the sum of mass of dry air plus mass of vapor. So if the concentration of water vapor within the parcel is changing, it will obviously change the molecular weight of the moist air that we are considering. So in each case, we will have to define a new R value, which compensates for the change in water. In order to avoid this, avoid the using of different gas constant for each constitution of moist air, what we did was we wanted to retain the gas constant for dry air, and then we introduced a new fictitious temperature called as a virtual temperature. So now R will remain RD itself even if we are considering moisture parcel. Temperature will change to a fictitious temperature, which is basically known as a virtual temperature. So that's how we introduced this new term, which is a virtual temperature. So virtual temperature is basically the temperature that dry air would have in order to have the same density as the moisture. So we have dry air and moisture, which is basically having different densities. Generally, the density of dry air is greater than the density of moisture. So if we consider, if you guys remember the mass of dry and moisture, in case of dry air, the mass was 20.6. In case of moisture, it was 18 point something. So basically, since the mass of dry air is more, the density will also be more for dry. So if we have to need a moisture air parcel, or if we have to make the density of the dry air parcel same as the density of the moisture air parcel, then we have to increase the density of the dry air, which is basically by heating the dry air. So that temperature that the dry air parcel have to attain to have the same density as the moisture is basically known as the virtual temperature. So since moisture is less than dry air at the same temperature and pressure, the virtual temperature is always greater than the actual temperature. So basically we have to heat the dry air so that it will have the same density as the moisture. So that temperature TV, the new fictitious temperature, virtual temperature will always be greater than the actual temperature. So the equation for TV is given by T by 1 minus E by T into 1 minus epsilon, where E is the vapor pressure of the water vapor, P is the total pressure of the parcel, and epsilon is a constant value which is having a value of 0.62. These things we have already discussed. So I just want to revise these things. So that is basically virtual temperature. So the question is, the virtual temperature depends on what? They have given different parameters. What all parameters the virtual temperature depends on? So the virtual temperature TV is basically given by T into, as we just saw, TV TV is basically T by 1 minus E by P into 1 minus epsilon. So E is the vapor pressure exerted by water vapor. P is the total pressure of the parcel. And epsilon is a constant which is defined by mv by md, rd by rb, etc. So that is epsilon. Okay. So now the question is, what does the virtual temperature actually depends on? So from the equation we can see it depends on the dry air temperature, which is actual temperature, capital T. And does it depend on any other of these parameters? So here we have a quantity known as the vapor pressure. So we have vapor pressure in our equation. If we let's try to substitute vapor pressure in terms of what is known as the mixing ratio of the parcel. So if you guys remember, mixing ratio is basically mass of vapor by mass of dry air. This is mixing ratio, which can be represented by R or W. I think in my live interaction in the previous sessions I have used the notation W. So you can use anything, R or W. Both are basically mixing ratio. So R is given by mv by mt. So basically the vapor pressure, the pressure exerted by water vapor on a parcel is basically the ratio of number of moles of vapor to the number of moles of to the total number of moles in that parcel into the total pressure. It is basically the pressure exerted by water vapor alone. So just like how much amount in the total pressure is actually contributed by the vapor. So it basically is directly proportional to the number of moles of vapor present in the parcel. So NV by number of moles of vapor by total number of moles in the parcel into the total pressure. So it is basically the ratio. This ratio basically gives the vapor pressure. Now from this we can write E is equal to number of moles is basically mass of water vapor by molecular weight of water vapor. Here also mv by capital MV plus ND is mass of dry air by molecular weight of dry air. So small mv is actually how much is present within the parcel, and capital MV is the molecular weight of the molecular weight of water vapor. So why we did this is basically to write E in terms of vapor pressure in terms of the mixing ratio R, which basically is the moisture concentration, which basically gives the moisture concentration in the parcel. So from this, if we multiply 1 by md, both numerator and denominator, small md, which is the mass of dry air, multiplying 1 by md, both numerator and denominator, mv by md can be written as R by mv is to mv divided by, here also mv by md can be written as R divided by capital MV plus md by md is 1 by m. It will become like this. Now again to simplify, we can into P. P is also there. So we are representing E in terms of P. Yeah. Now in order to simplify this, again what we can do is we can multiply by mv, both numerator and denominator. So again we are multiplying mv, capital MV, both numerator and denominator. So this mv will be gone, so it will be R by, here also mv will be gone, R plus mv by mv. So as I said, mv by mv is basically the molecular weight of vapor, which is 18.016, divided by mass of dry air as 28.9, giving a value of 0.62. We have already discussed how to calculate the mass of vapor and mass of dry air based on the constituents of the parcel. We have already discussed these things. So this is the value that we got when we calculated the mass of vapor and mass of dry air. So substituting these, we will get a value 0.62. So it is 0.622 R by R plus 0.622 or epsilon. So this is basically epsilon into P. So that is the relation between E and R. E is equal to R by R plus epsilon into P. So in the virtual temperature equation we have vapor pressure, but we don't have the value, we don't have R. So what we can do is we can substitute the value of E in terms of R into the virtual temperature equation. So virtual temperature equation is given by TV is equal to 1 minus E by P into 1 minus epsilon. Just now we got E is equal to R by R plus epsilon into P, which implies E by P is equal to R by R plus epsilon. Okay, now we substitute. TV will become T by 1 minus E by P will substitute R by R plus epsilon into 1 minus epsilon, which is equal to T into R plus epsilon by R plus epsilon minus R plus epsilon R. which will become Rn minus R will become T into R plus epsilon by epsilon into 1 minus R. Sorry, 1 plus R. It will become like this one after simplifying. So now here again, in order to simplify, 1 by 1 plus R, 1 by 1 plus R can be written as 1 minus R by 1 plus R into 1 minus R. Both numerator and denominator we are multiplying by 1 minus R. So this will basically become 1 minus R by A plus B into A minus B, 1 minus R square. So this will be substitute. TV is equal to T into R plus epsilon by epsilon. This 1 by 1 plus R we are going to substitute 1 minus R by 1 minus R. Instead of 1 by 1 plus R, we substituted 1 minus R by 1 minus R. Now again, if we open the brackets, it will be T into R minus R square plus E minus R epsilon by epsilon into 1 minus R square. So mixing ratio is basically mass of vapor by mass of dry. So mass of vapor will be very much small when we are comparing with the total mass of dry air. So this will be having values like very less values actually in terms of gram per kilogram. So when we are squaring these terms, R square will be very much less. The value of R square will be very much less, such that we can ignore the value of R square. So because value of R is very less, we can ignore the second order terms. So it will become T into R plus epsilon minus R epsilon by, so we ignore the terms which is having R square. So it will be like this. TV is equal to R plus epsilon minus R epsilon by epsilon. So this can be written as TV is equal to T into TV epsilon is equal to TR, will open the bracket, plus epsilon T minus TR epsilon. So it comes TV epsilon is equal to TV epsilon minus epsilon T is equal to TR into 1 minus T epsilon into TV minus T is equal to TR into 1 minus, which will give you TV minus T is equal to TR into 1 minus epsilon by epsilon, which is the value of 1 minus epsilon by epsilon will give you 0.61. 1 minus 0.622 by 0.622. That is the value of 1 minus epsilon by epsilon, which is basically 0.61. Yeah, so we reach TV is equal to T are 0 point, not TV minus T. TV minus T is equal to TR 0.61. So TV is equal to T plus TR into 0.61, or TV is equal to T into 1 plus 0.61 R. So this is the equation of virtual temperature in terms of R. R is the mixing ratio. So even though initially we felt like it doesn't depend on the mixing ratio, finally we found that it depends on both the dry air temperature and the moisture concentration. So virtual temperature is dependent on both moisture concentration and dry air temperature. So this was the first equation. From this, after substituting in the equation for virtual temperature in terms of R. R is the mixing ratio. I have already done this derivation in the previous class. Just for revising, I did it again. Okay. So that's all about virtual temperature. Now, the next question is, the heat supplied to ideal gas at constant volume is equal to what? Change in temperature, change in pressure, change in internal energy, or is it basically equal to 0? Heat supplied to ideal gas at constant volume. So basically how the heat supplied to an ideal gas is distributed is given by the first law of thermodynamics. According to the first law of thermodynamics, dQ is equal to du plus dW, where du is the internal energy change, dW is the work done. dQ is the heat supply to the system. So this is dQ is equal to du plus dW. So there were different forms of this first law of thermodynamics, if you guys remember. So there was we have discussed the different forms of thermodynamic equation. So this is a basic equation which shows dQ is equal to du plus dW, and then in terms of work done, pressure volume work, that is dQ is equal to du plus P d alpha. Then in terms of specific heat constants, so specific heat constant volume, it was dQ is equal to Cv dt plus P d alpha. And then in terms of specific heat at constant pressure, it was Cp dt minus alpha d. These derivations we have already discussed in previous classes. So these are 4 different forms of the first law of thermodynamics. In this question, which one we should use? So in this question, they have mentioned the heat supplied to ideal gas at constant volume. So constant, the heat is being supplied at constant volume. So then this equation, specific heat constant volume, will come. So dQ is equal to Cv dt plus P d alpha. So from this, so dQ is equal to Cv dt, or basically du. So from here, it is basically equal to Cv into dt. Not exactly change in temperature, but change in internal energy. So from here it is dq is equal to cv dt plus p d alpha. So they have given the volume as constant, which means d alpha will be 0. So in that case, dq will become cv dt. So cv dt is basically the change in internal energy. This also we have discussed before. So the change in the heat supplied is directly used to change the internal energy of the system. So it is not. So this will be the answer to the question. It is change in internal energy. So from the first law of thermodynamics, we know dq is equal to cv dt plus pd alpha. Since the heat is being supplied at constant volume, the change in the specific volume d alpha will be 0. So the equation reduces to dq is equal to cv dt. cv dt is nothing but the internal energy of the change in the internal energy of the system, which is d. So the answer to the question is change in internal energy. So now the next question. So on moving from mid-latitude to tropics, the mixing ratio in the atmosphere. What happens to the mixing ratio in the atmosphere? So we are moving from mid-latitude. So if you guys remember, we have discussed this before. This is 0 degree, which is the equator. Then we have 23.5 degree north, 23.5 degree south, which is Tropic of Cancer and Tropic of Capricorn. So this region is basically known as the tropics. Above this, we have the mid-latitude. So the tropics is basically near to the equator. So when we are moving from mid-latitude to the tropics, what happens to R? Mixing ratio is given by mass of water vapor to mass of dry. So basically in the tropics, comparatively, the temperature will be high. So when the temperature is high, it basically means it can hold more moisture. So this is because if we have a puzzle like this that has different air molecules. So this is such a temperature T1. Now consider there is another parcel which is such a temperature T2. In that case, the temperature is more, the air parcel will expand. So there will be more space between the air molecules, or as the parcel is expanding, empty spaces within the parcel will increase. So the parcel basically can hold more water vapor, more moisture. So when the parcel is expanding or when it is warmer, it means the capacity of holding moisture also increases. So basically when we are moving from mid-latitudes to tropics, so the capacity of holding moisture is basically given by the mixing ratio. If the capacity of holding moisture will be high, MV will also be high, R will also be high. So as we are moving from mid-latitudes to tropics, the temperature is increasing such as the mixing ratio. So this is the answer. It basically increases as we are moving from mid-latitudes to the tropic. The mixing ratio in the atmosphere increases. Now, the next question is the internal energy of a sinking air parcel. Sinking in the sense which is moving down in the atmosphere. So first let us consider the condition for a rising air parcel. So as we know, as we are going up, the pressure is decreasing in the atmosphere. So if this is the pressure at the surface, as we go up, the pressure is decreasing. If the pressure is decreasing, the volume will increase since it is having an inverse relationship. So this is the volume. This will be the volume at pressure P2. This is P1. This is P2. Volume will be high as the parcel is rising. So as the parcel is rising, so basically the pressure of the environment, the pressure of the parcel should match each other. It will be equal. It should be equal to attain equilibrium. So as the parcel is moving up, the pressure is decreasing. The pressure is decreasing. The only way to make the pressure of the parcel equal to that of the environment is to increase the volume so that it will be compensated. So that's why this expansion is happening. So basically the internal energy du is given by Cv dt. So as the parcel is rising, the parcel is doing an expansion work, right? So during expansion, uh, basically the parcel is doing work. So there will be decrease in temperature. Temperature will decrease, which means internal energy will also decrease. Now if we are considering a parcel that is coming down, so this was the initial, now it is coming down, so this is the final. V2, V1, V2, V1, V2. In this case, pressure is increasing, so in order to match, volume should decrease. So volume is decreasing, so the work is done, there is compression happening. Work is done by the surroundings on the system. So du is equal to Cv dt. Since it is compression, temperature will increase. The work is done on the system, not by the system. So there will be an increase in temperature. So du will also increase. So in this is in case of a rising parcel. This is in case of a sinking parcel. So here the question is, in case of a sinking parcel, what is happening? So in case of a sinking air parcel, as it is coming down in the atmosphere, its pressure is increasing. It will lead to, if the pressure is increasing, it will lead to a decrease in its volume. So since it is compression or the work is actually being done on the system, there will be a decrease in temperature. So the internal energy which is given by Cv dt will also increase. So the internal energy of the system will increase in case of a sinking air cell. The next question is, which of the following does not help in the convection of the air? So convection is basically the rising of the parcel. Convection is happening. So there are different ways, different types of convection. First one is convergence. So basically, if there is a low pressure area in the surface, if this is low pressure, surroundings there will be high pressure. So basically, the air or the wind blows from high pressure to low pressure. So the wind from the surroundings will start blowing towards this low pressure region. So it will lead to a convergence at the surface. So this is one of the convection type. Okay. So this convergence of air at the surface will help in the convection of the air. So this is not the answer. So convergence will lead to is the type of convection. If there is convergence, it will lead to rising particles. The air will start converging or accumulating in the surface, then it will rise. So that is convergence. Now the second convection type is Fresnel convergence. Suppose there is a cold air mass and there is a warm air mass. What happens? These two air masses are approaching each other. As it approaches each other, the cold air mass, which is having a lower density, higher density, will sink, and the air parcel, which is having warm air and having a lower density, will be lifted as it approaches. The cold air will go down and the warm air will be uplifted. So this will also lead to rising of air parts. The warm air is being lifted from the surface. So this is another type of convection. Third one is due to thermals. Suppose there is a heating that is local heating that is happening over the surface. The surface parcels in the surface of there is a heating that is happening. The air parcels will the temperature of the parcel will increase, which will lead to density decrease in density, and the parcels will lead to a rising motion. This is known as thermals due to surface heating. This will also lead to convection of the air. Now the fourth one, so this is also not the answer. Surface heating also is not the answer. Fourth one is topographic lifting, orographic lifting. Orographic lifting. Orographic lifting, what happens is that suppose the air is coming like this. Now this it encounters this barrier. Topography means which is at a higher altitude, like which is having a higher altitude. So in that case, it will this thing is blocking the air. So what happens is that as it reaches here, it will start going up since it don't have any other way to cross it. It will start going up. This will also lead to convection. So that this is also not the answer. The question is basically which does not help in convection of the air. So this the final answer is divergence. So when there is divergence at the surface, it won't lead to convection of air. So when there is divergence, like air is going like this, then here there will be a sinking motion instead of convection. Okay. So yeah, that is about different types of convection. Now the next question. The condensed air parcel cools more slowly because of. So condensed air parcel in the sense there is a saturated air parcel. Saturated in the sense the parcel is holding the maximum amount of water vapor that it can. So once the parcel gets saturated, this condensation process will start to okay. Yeah, I can repeat Frenkel convergence. So Fresnel convergence means there are two air masses. So suppose one is a cold air mass and basically air masses with different temperature. Okay. So there are two different air masses which is having different temperatures, and these two air masses are approaching each other. So different temperatures in the sense one will be cold and the other will be warm. So these will be having different densities as well. Just like different temperatures, it will be having different densities. So as these two air masses are approaching each other, once they meet, what happens is that this cold air mass, which is having a lower temperature as well as higher density. The temperature will be less and the density will be high. This will actually go down because of its higher density, and the warm air, which is having a higher temperature and lower density, will go up. It will be lifted. So the cold air mass will go down and the warm air mass will go up. Like when they meet, the warm air mass will be uplifted. So that happens. That is basically known as a Fresnel convergence. So when air masses of different temperatures meet each other, the air mass that is having a lower temperature and higher density will go down, and the warm air mass which is having a higher temperature and lower density will go up. Then at that meeting point also convection happens. So the Fresnel systems is the reason for this is reasons for rainfall and all in mid latitude regions. This is not seen that much over the tropics, but over the mid latitudes and all, this Fresnel convergence is one of the reason for convection and rainfall. So this is basically when two air masses of different temperatures and densities meet each other. What will happen? One air mass will go down, which is having a lower temperature and higher density, and the warmer air mass, which is having a higher temperature and lower density, will go up. It will be going like this. So that will also lead to upliftment of air and convection. Is it clear? Oh, yeah. Fine. Okay. So yeah, that is about different convection types. Now let's move on to the next question. So the condensed air parcel cools more slowly because of, so as I said, condensation happens when the air is saturated. Saturated means the air is already holding the maximum amount of water vapor that it can contain. So once it has reached that saturation level, then the water vapor will basically starts to condense. So when condensation is occurring, condensation means the vapor is becoming water. Water droplets or water is formed. So a phase change is occurring here. Phase change. So whenever there is phase change, there will be release. There will be latent heat formation. So in this case, the phase change is basically vapor to liquid. Vapor to liquid. So there will be latent heat release. Latent heat release will be there in this case. So here, in case of air parcels, in case of vertical motions of air parcels, we have told that initially when we did the assumptions, we are considering all processes to be adiabatic. Adiabatic is in the sense the whatever heat is, the dq will be zero. No heat is not added or removed from the system. So whatever heat is being produced within the system will not go out, but instead will heat the system itself. So in this case, whatever the latent heat that is being released will be used to heat the parcel itself. So what happens is that the condensed air parcel, the rate at which the condensed air parcel cools, dt by dz. So if the air parcel is moving up in the atmosphere, as it goes up, the temperature will be decreasing. We have learned this before. So in this case, the rate at which the temperature will decrease is to some part compensated by the latent heat release. So this latent heat release actually tries to reduce the rate of cooling of the air parcel. So as the parcel is going up, it will encounter the decrease in temperature with respect to height. But in the case of a condensed air parcel, what happens is that there is this vapor to water conversion that is happening within the system. So, and there is a latent heat release. So this latent heat release will partly compensate the decrease in temperature that is happening due to the vertical movement of the parcel. So the answer is latent heat release. Because of this, the condensed air parcel cools more slowly compared to a dry air. Now, the next question is, which of the following thermodynamic quantity remains constant during an adiabatic process? So, the process in which the temperature is constant is basically known as an isothermal process, in which pressure is constant is known as isobaric process, in which volume is constant is known as isobaric process. So these are the different processes in which these quantities are conserved or these quantities remain constant. Now the only option that is left is potential temperature. So during an adiabatic process, potential temperature is the quantity that remains constant. We know that adiabatic process means dq will be zero. There is no heat added or heat doesn't enter or leave the system. This is the basic idea of adiabatic process. So since dq is zero, the first law, let's try to prove this actually, that during an adiabatic process, potential temperature remains constant. This thing I haven't taken earlier, so I just want to cover this out. So according to the first law of thermodynamics, dq is du plus dw. So du is basically cv dt that we already know that, and dw is pdr. So dq is cv dt plus pdr. So dq is equal to 0 means Cv dt plus P d alpha is equal to 0. This is what it means basically. So let it be equation number 1. So yeah, one more thing. What is basically the potential? So potential temperature is the only quantity that is remained. So what is basically potential temperature? So potential temperature basically of an air parcel is defined as the temperature that the parcel would have if it were expanded or compressed adiabatically from its existing pressure and temperature to a standard pressure P0. So suppose the parcel is at a pressure P and temperature T. So we will either adiabatically expand or compress the parcel, and then bring it down to the standard pressure 1000 hectopascal, and then we are trying to find what is the temperature of the parcel when it reaches this particular pressure level. So that temperature is known as the potential temperature. Okay. So that is the basic definition of potential temperature. So during an adiabatic process, the potential temperature remains constant. So just now we found that adiabatic process means Cv dt plus Pd alpha will be 0. That's equation number 1. Now from ideal gas equation, P alpha equal to R. Now if we differentiate this, Pd alpha plus alpha dp is equal to R. R is a constant, so only dt will have the differential. Now if we multiply with Cv, it will become Cv Pd alpha on both right hand side and left hand side. Cv Pd alpha alpha Cv alpha dp C is equal to Cv R dt. Now Cv plus R sorry. Yeah. So from the ideal gas equation, P alpha is equal to RT. Then differentiating it will become P d alpha plus alpha dp is equal to R d dt. So dt is P d alpha plus alpha dp by R. Okay, this is equation 2. Now we are substituting the value of dt in the first law, the equation for first law of thermodynamics in case of an adiabatic condition. In that case, equation 1 will become Cv into P d alpha plus alpha dp by R plus P d alpha is equal to 0. Okay. Now CVR P d alpha plus Cv P d alpha Cv P d alpha plus Cv alpha dp plus R P d alpha is equal to 0. from here we can write CV plus R into P d alpha plus CV alpha dp is equal to 0. CV plus R is basically C or Cp minus Cv is equal to R. This is a known relation. So if we substitute it here, Cp into P d alpha plus Cv alpha dp is equal to 0. Now if we are dividing, we just got Cp into P d alpha plus Cv into alpha dp is equal to 0. Now if we are dividing by CVP alpha, the whole thing. So it will become Cp by Cv, P and P will be gone, into d alpha by alpha plus Cv will be gone, alpha into alpha and alpha will also be gone, dp by p is equal to 0. dp by p plus Cp by Cv into d alpha by alpha is equal to 0. Cp by Cv, these are also constant, it can be written as gamma. So then gamma into d alpha by alpha plus dp by p is equal to 0. Now on differentiating this equation, integrating this equation, it will be integral dp by p plus gamma integral d alpha by alpha is equal to 0. Integral of dp by p is log p plus log alpha raised to gamma is equal to a constant, or p by p alpha raised to gamma is equal to a constant. This is the mathematical expression for an adiabatic process. Okay, p alpha raised to gamma is equal to a constant. We derived it from the first law of thermodynamics. P alpha raised to gamma is equal to constant. This is the mathematical representation of an adiabatic process. Now what we want to do, we have to prove that during an adiabatic process, the potential temperature remains constant. So for that, we will start from here. So we just obtained the mathematical expression for an adiabatic process, which is P alpha raised to gamma is equal to a constant, where gamma is equal to Cp by Cv. So P alpha is equal to RT from ideal gas equation. So alpha can be written as RT by P. Now if we substitute it here, it will be P of RT by P, the whole raised to gamma is equal to a constant, and P raised to 1 minus alpha into RT whole raised to gamma is equal to a constant. Now R raised to gamma is also a constant. So P raised to 1 minus gamma into T raised to gamma is equal to a constant. So if we take R raised to gamma to this side, that is also a constant. So Cp by Cv is basically gamma as I told you. So from this we can write P of, so if we divide the whole thing by gamma, the whole power we are dividing it by gamma, it will become 1 minus gamma by gamma into t. E raised to gamma by gamma will be, let's call this constant k2. So 1 minus gamma by gamma it will become. So P of 1 minus Cp by Cv is basically. So Cv minus Cp by Cp by Cv into T is equal to K. Cp minus Cv is R minus R by Cp into T is equal to a constant K. So P raised to minus R by Cp into T is equal to a constant. Now, when we look at the, let this be equation 3. So this one we got from the mathematical expression for the adiabatic process. P alpha raised to gamma is equal to constant. We substituted alpha from the ideal gas equation. Then R raised to gamma was also taken to the right hand side, and then another constant K2 we defined. Then finally we got the expression P raised to minus R by Cp into T is equal to a constant, that is the K2. Now the just give me a sec. Yeah. Now so we just got Pa raised to minus R by Cp into T is equal to a constant K. We got this expression. Now potential temperature is basically theta is equal to T into T0 by P the whole raised to R by C. This is the equation for this is the equation for the potential temperature. Where theta is the potential temperature, T is the actual temperature, T0 is the standard pressure which is 1000 MB, and P is the pressure of the flask. From this we can write theta is equal to, if P0 is considered to be constant, we can write T into P raised to minus R by Cp. We can write it in the as equal to theta is equal to T P raised to minus R by Cp is equal to a constant into K. So this will reduce to this form. T into P raised to minus R by Cp is equal to constant, which basically means theta is equal to a constant. So the potential temperature remains constant during an adiabatic process. We just proved that. So here what we did, we just wrote the equation for potential temperature. So in this case, P0 is equal to a constant. So then this will reduce to P raised to minus R by Cp. Theta is equal to T P raised to minus R by Cp. That is also a constant. So theta will be constant. Then during an adiabatic process, the potential temperature remains constant. Okay. So now the next question. The Brent frequency represents the. So what does Brent-Weisshaller frequency? Brent frequency is n square is equal to G by Te into gamma d minus gamma. Suppose gamma d is greater than gamma. Gamma d is greater than gamma in the sense the rate at which the this is ELR, environmental lapse rate, or gamma, and the dry adiabatic lapse rate is greater than gamma. So the rate at which the temperature of the parcel is reducing is greater than the environmental lapse rate. So it will be like this. This will be gamma. If we look at some particular height, the temperature of the parcel, this height, the parcel is having a lower temperature compared to that of the environment. So this will have a tendency to sink. So gamma d greater than gamma, and n square will be greater than 0, or n square will be positive. N square will be greater than 0 if gamma d is greater than gamma. In that case, this is a differential equation corresponding the change in delta set change in the vertical displacement and the Brent-Weissala frequency n square. So this is the second order differential equation, delta set double dot. So d square delta set by, in this case n square is positive, delta set will have a value of the solution will be of the form a cos nt plus b sin nt. So this basically represents an oscillatory motion. And in the second case, when gamma d is, so this basically represents a stable condition. The dry adiabatic lapse rate is greater than gamma. The parcel cannot rise, it will have that sinking tendency. This basically represents a stable condition. Now, when gamma d is less than gamma, which means the rate at which the temperature of the parcel is decreasing, that's lower than the environmental lapse rate. In that case, n square will be less than 0. So if we solve the differential equation, it will have a solution. Delta set is equal to a e raised to n. These are the standard solutions for the second order differential equation. It will have this form in case of unstable um, atmosphere. So this is not an oscillatory motion. So the Brent-Weissala frequency basically represents a stable atmospheric oscillation. This is the answer. It basically represents, it corresponds to stable atmospheric oscillation. So earlier in the previous classes, if you guys remember, we have talked about the term called static stability. That's how this Brent-Weissala frequencies came into. We define the Brent-Weissala frequency in terms of static stability. So in that case, what we did was we considered a layer in the atmosphere in which the actual lapse rate gamma was less than gamma d, or gamma d is greater than gamma, just like as I told now. So this is the environmental lapse rate. This is gamma. This was gamma. This was the condition. So now there was an initial point O. We tried to rise the parcel from O to a height A. Okay, so in that case, this will be at the height A, this is the temperature of the environment, and this is the temperature of the parcel. So TA is less than T environment. So what will happen? The parcel will have the tendency to come back to its initial position O. We are trying to rise the parcel, but because the temperature is less than the environment, it will have a tendency to come back to its initial position. Now suppose if we are displacing this parcel from O to a lower height, who's here, let it be C. In that case, this is the temperature of the environment, and this is the temperature of the parcel. In this case, the parcel temperature is greater than the environment temperature. So what happens? The parcel will have a tendency to rise. So again it want to go back to its initial position. So in this case, this condition basically when the parcel has a tendency to go back to its initial position, it will kind of oscillate in its initial position. So the frequency of these oscillations is known as the Brent-Weissela frequency. So this basically comes into play in a static state and an environment which is having a positive static stability. And it is having the condition the lapse rate, dry adiabatic lapse rate is greater than the environmental lapse rate. The parcel is cooling at a higher rate than the environment. In that case, the parcel will have a tendency to oscillate from in its initial position itself, or it has a tendency to come back to its initial position. So it will start oscillating with respect to that initial point. So that the frequency of those oscillations are known as Brent-Weissela frequency, and it is given by the equation n square is equal to G by T into gamma T minus gamma. Okay. Now the next question. Suppose the environmental lapse rate is faster in comparison with the parcel lapse rate. Just like we discussed now. This is also regarding the lapse rate. So the question is environmental lapse rate gamma is greater than the parcel lapse rate gamma D. The parcel displaced from its mean position. So gamma is environmental lapse rate. Let this is gamma. So they have given gamma is greater than gamma. The rate at which the temperature is decreasing in the environment is greater than the rate at which the temperature is decreasing for the parcel. So let this be gamma B. So in that case, if the parcel is displaced from the mean position, what will happen? So let this be the starting point. Initially this was the parcel's point. So now it is raised to this point. So this height. So at this point, the temperature of the parcel is this, TA. And this is the temperature of the environment, TB. So TA is greater than TB at this particular point. So TA is the temperature of the parcel. Temperature of the parcel is greater than temperature of the environment. So the parcel will basically have a tendency to rise. This is the answer. So if the environmental lapse rate is faster in comparison to the parcel lapse rate, the parcel displaced from its mean position will have a tendency. Okay. So this is the answer. Now the next question. The dry static energy of an air parcel will be what? What is basically the dry static energy of an air parcel? We have discussed this in the thermodynamics. Dry static energy of an air parcel is given by H plus phi, where H is the enthalpy of the parcel and phi is the geopotential. So the enthalpy is basically Cp into T, and phi, the geopotential, is defined as G T. So the dry static energy is Cpt plus G into Z. So they are asking what is the dry static energy of an air parcel. In case of air parcel, you can write dt by dz is equal to minus g by c. So as the parcel is moving, this is the lapse rate of the parcel. So this has so dt by dz is equal to minus g by c. This corresponds to a dry air parcel as the parcel is undergoing vertical motion. So dt by z is equal to g by cp. Now we can write cp dt is equal to minus g dz, or cp dt plus g dz is equal to 0. For a differentiate this, d of C3 dt plus g reset will be a constant. So the dry static energy of an air parcel will be this is the okay. Now I think we have two numericals. After that we will end today's session. The first numerical is an air parcel that has a temperature of 20 degrees Celsius at 100 MB level is lifted dry adiabatically. What is its density when it reaches 500 MB level? So there is a parcel so there is an air parcel which has a temperature of 20 degrees Celsius at 1000 MB level. Sorry, it is not 100, it is 1000. At 1000 MB level, this is the temperature of the parcel. This parcel, we are lifting it dry adiabatically to the layer 500 MB. So what will be the density of the parcel at this height? That is the question. So dry adiabatically lifted in the sense the potential temperature will be constant as we just discussed. Dry adiabatic process, potential temperature theta will be a constant. That is theta, which is defined as T into P0 by P, the whole raised to R by Cp, will be a constant for 1000 MB as well as 500 MB. The value will be the same. So in case of 5000 MB, we can write Ps into P0 by Ps, the whole raised to R by Cp will be equal to T into P0 by P, the whole raised to R by Cp. This is for the surface and this is for the pressure level P. So from ideal gas equation, we can write P is equal to rho R T, or T is equal to P by rho into R. We substitute it will become. So basically we want to find the density of the parcel, right? Rho. So it will be Ts P0 by Ps, the whole raised to R by Cp is equal to, instead of T we can write P by rho R into P0 by P, the whole raised to R by Cp. Now if we write for rho, which is the density of the parcel at pressure P, rho will become Ps P by Rts into P0 by P, the whole raised to R by Cp minus 1. R by Cp is having a value of 0.28. So R by Cp minus 1 is having a value of 0.72. So rho will become 10 raised to 5, which is P by So it is basically PS by RTS into PS by P the whole raised to R by Cp minus 1. So PS is basically 10 raised to 5 by R is 287 is 7 into temperature is given as 20 degrees Celsius. In Kelvin it will be 298. PS by RTS into P0 by P, just 1000 hectopascal, just 1000 into 10 raised to 2 pascal, 500 hectopascal, just 500 into 10 raised to 2, whole raised to minus 0.9 R by Cp minus 1. So it is plus 0.7. So it is plus 0.7. The value of R by Cp minus 1 is 0.7. So rho will have a value of 10 raised to 5 divided by 287 into 298 into 1000 by 500, which is basically 2 raised to 0.7. So basically give you a value of 0.725 kilogram per meter. So how did we get this? So basically they have given an air parcel which is having a temperature of 20 degrees Celsius at 1000 MT level is left a dried air practically. So what will be the density when it reaches 500 MT level? So basically the potential temperature of the parcel will remain constant. So since the process is dry adiabatic, so we wrote the equation for the potential temperature, which is T into P0 by P the whole raised to R by C. So it will be PS. PS and P0 are the same thing. Just generally P0 is considered to be 1000 MT. So we can write for the surface the potential temperature will be Ts into PS by PS the whole raised to. And in case of 500 MB surface, we can write T into T0 by P the whole raised to R by C. Now T we can substitute using, we basically want to find the density of the parcel. So here we don't know what is in this equation we don't have the density value. So we can substitute the equation for density from ideal gas law. So T is P by rho R. So if we substitute T here, just P by rho R, it will become Ts into PS by PS the whole raised to R by Cp is equal to P by rho R into P0 by P the whole raised to R by Cp. Now after rearranging, rho will become PS by RTS into PS by P the whole raised to R by Cp minus 1. So R by Cp, R and Cp are constant. So R by Cp is having a value of 0.28. Now if we want to find R by Cp minus 1, it's just having a value minus 0.7, minus 0.728. Now if we substitute all values in this equation, we will finally get the value of rho to be 0.725 kilogram per meter. That is the density of the air at 500 MB. Now the last question. Suppose water vapor with a methane vapor with a mixing ratio of 5 per kilogram, and the total pressure is 1026.8 hectopascal. What will be the vapor pressure? So the question Air contains water vapor with a mixing ratio R is given 5.5 gram per kilogram. So R and W are the same. I have used the notation W earlier, so that's why I'm telling this. It's the same thing. Just both is used for mixing ratio. This is basically 5.5 into 10 raised to 5. 5.5 into 10 raised to minus 3 kilogram per kilogram in SI unit. And the total pressure, which is P, is given by 1026.8 that's which is 1026.8 into 10 raised to 2 pascal. Now the vapor pressure P is equal to pressure. So R is basically epsilon into E by P. This is the equation for mixing ratio. So we have derived this equation earlier. If you remember, we found the relation between E and R while deriving crystal temperature. We found that E is equal to R by R plus epsilon into P, or E by P is equal to R. Since the value of, so this was the equation that we got, E is equal to earlier we derived the equation E is equal to R by R plus epsilon into P, or E by P is equal to R by R plus epsilon. Basically the value of R is very less. It's very much small than E. So as we can see here the value of R is 5.5 into 10 raised to minus 3. And the value of E is basically 0.62. So it is very much less. So R plus E, the denominator term, R plus epsilon is approximately epsilon. So then we can write E by P is equal to R. Epsilon into R. That's how, R is equal to epsilon into E by P. That's how this equation. So R is equal to epsilon into E by P, which is basically 0.622 into E, vapor pressure, which is, we have to calculate E basically. E is equal to RP by epsilon. R is 5.5 into 10 raised to minus 3 into total pressure 1026.8 into 10 square divided by epsilon is 0.62. That's the answer. Five point five into 10 raised to minus 3 into 1026.8 into 10 square divided by 0.62 will give you a value of 907 pascal. 907.9 pascal or 9.07 hectare. This is a vapor pressure. So if there is a moisture air parcel with the total pressure 1026.8 hectopascal and having a mixing ratio of 5.5 gram per kilogram, the pressure exerted by the vapor on that parcel will be 9.07 hectopascal. That is the vapor pressure. So that's it. I just want to revise the concepts that we have already learned. Yeah, so I think we will have the last session on this Saturday. That's it for today. Thank you. We will end the session here. If you guys have any doubt, you can ask. Otherwise, we will